Today we have just one lecture, lecture 21, because you took the gateway exam. We have our regular exam 2 coming up on Wednesday of next week. Next Monday we will review through that exam. And so the new content goes through what is new today on that exam. The topics are going to be more on linearization. We're going to still keep doing linearization pretty consistently here, even after exam 2. It's a pretty important thing. We're going to touch on something called a higher degree polynomial approximation, also called a Taylor series approximation, or Taylor polynomial, if you've ever heard of that. We're going to talk about a few theorems: the increasing function theorem, the decreasing function theorem, and the constant function theorem, and some applications. Those theorems are in section 3.10. It's a pretty theoretical section. I'm not going to test you on everything in that section for exam 2, but other things in that section could come up for exam 3. And then if we have time, which I'm doubting a little bit, we'll do implicit differentiation again. Okay? If we don't have time for today, we'll come back to it for sure next Monday and do another exam. Here are some standard linear approximations that, well, you don't really have to memorize for the test because, well, for one thing, you can use a note card on the test. But I probably wouldn't test you on memorizing these things anyway. However, they are something that you should perhaps work on memorizing for the future. If you need more math classes, or you need physics classes, or physical chemistry, or other kinds of classes where you use a lot of calculus-related math, these are probably worth trying to memorize to some degree at least. For e to the x, near x equals 0, here is a standard linear approximation. E to the x is approximately 1 plus x when x is approximately 0. And with each of these things, you can pretty quickly verify them by using the formula for the tangent line approximation. Local linearization, L of x is f of a plus f prime of a times x minus a. For most of these, a is going to be 0. You don't see an a in there, but it's implied. The 0 is what a is. Okay, so when you say near x equals 0, or when x is approximately 0, that is meaning you are taking the a to be 0. So for this example, the function f of x is e to the x. That's nice and easy, and that means f prime of x is also e to the x. Plug in a equals 0. In both cases, you get 1. And therefore, when you plug these things in here, again using a equaling 0, this becomes 1 plus 1 times x minus 0. In other words, 1 plus x. Which is what you see on the screen here, 1 plus x. So there's your tangent line approximation to e to the x near x equals 0. In other words, using a equals 0 as the point at which you find the equation of the tangent line. There are going to be infinitesimal analogs of these things as well. And what do we do with infinitesimals, dx's? Well, if you see any dx squareds or dx cubes or dx to the fourth, you make them go away. You essentially treat them as 0. There are no squared terms here, so we're not going to have to worry about that. The other thing you do is you actually make it an equality like that. E to the dx is 1 plus dx, exactly when dx is infinitesimally small. Now again, this is just pretend math in a sense, right? If we were doing rigorous math with infinitesimals, it would be too hard. So when you imagine the idea of an infinitesimal, realize that with the standard real number system, there really is no such thing as an infinitesimal. There's no number that's positive yet smaller than every positive number. Because you can, for example, always divide it by 2 or divide it by 3 and make a smaller one. So it's just an imagination tool. And as an imagination tool, you go ahead and you just dispense with the approximately equal to. You say it's equal to it. Okay? I would encourage you, at least a few of these after class, to get your calculator and give it a try. You know, try e to the 0.0001 or something. You get about 0.00. Oh, excuse me. You get about 1 plus 0.0001 because the approximation is 1 plus x. What about the sine function? The sine function, sine of x is approximately equal to x when x is near 0. I could do the exact same kind of calculation, maybe I should, real quick here, with the sine function. If f of x is the sine function, then its derivative is the cosine function. F of 0 is sine of 0, we know that's 0. F prime of 0 is cosine of 0, that is 1. We're using a equals 0, that's implied here. So the approximation becomes 0 plus 1 times x minus 0, which is just x. No constant term. That's not so surprising when you think about the graph of sine of x. It's got a vertical intercept of 0, the constant term has to be 0. It is approximately equal to y equals x when x is approximately equal to 0. These graphs are very, very close together. If you zoom in on the sine graph, it's going to look more and more like the graph of y equals x as you zoom in toward the origin. If you replace the x with dx in infinitesimal, you get an exact equality, okay? We don't bother with the approximate equal to. Even though you might say this is technically not right, maybe, well, again, actually, infinitesimals don't exist in the standard real number system anyway. It's just an imagination tool that helps you derive things in calculus in a more fun way, avoiding limits. That's kind of the main thing. But it also gives you, it's more than just about avoiding limits and having fun. It's also intuition that helps in science and engineering classes. It will help with integrals as well, we'll see later on. What about the cosine function? Cosine of x is approximately 1 when x is near 0. Let's quickly do the cosine calculation. Back over here. If f of x is cosine of x, then its derivative is negative sine of x. Plug in 0 into those. Cosine of 0 is 1. Negative sine of 0 is still 0. A is 0. Plug in, you get 1 plus 0 times x minus 0. That's just 1. There's no linear term. The cosine graph looks like this. It's got a horizontal tangent there at x equals 0. Horizontal tangent whose output is 1. The slope there is 0. That's why there's no linear term in this approximation. If you replace x with dx, you just write an exact equality. And dx is infinitesimal. Square root of 1 plus x. It's approximately 1 plus 1/2 x. Give it a try. Try taking the square root of 1.1. Get your calculator out and try it. It's about 1.05. Pretty close. 1 plus 1/2 times 0.1 is what I'm getting at. Write that down. Square root of 1.1 is approximately, by this approximation, 1 plus 1/2 times 0.1. 1 plus 0.05 is 1.05. It's pretty close. In reality, it's closer to 1.0488. But if you round into 2 decimal places, it's pretty close to 1.05. It gets better as x gets smaller. Try square root of 1.01. Make this a 0.01. And that's a 0.01, and this gets an extra 0 in there. And the approximation is even better if you check in your calculator. Okay? The 1/2 here, in a sense, matches the fact that we're doing a square root. A second column. That's no coincidence. In terms of infinitesimals, you write it with an equality. 1 plus x to the p, where p could be any, well, let's take it to be a positive number, any positive number. Turns out to be approximately 1 plus p times x. And when p is 1/2, that would match this one. When p is a third, so you're taking the cube root of 1 plus x, you get 1 plus 1/3 x. If p was 1/4, so you're taking the 4th root of 1 plus x, you get 1 plus 1/4 x. But this works when p is 3/2 as well, for example. Or 7, or whatever, any positive number. There is in terms of infinitesimals, just change the approximately to an exact equal. And emphasizing p times x here without a dot, that's understood to be p times x. I'm really trying to emphasize this p times dx there by putting a dot in. You should be okay with it if I did not put a dot in. Natural log of 1 plus x turns out to equal approximately x when x is close to 0. That also means, by the way, that natural log of x, since x could be thought of as 1 plus x minus 1, little trick, would be approximately equal to x minus 1 when x minus 1 is approximately 0. In other words, when x is approximately 1. Still a little trick there. Natural log of x. X is the same as 1 plus x minus 1. Now treat the x minus 1 here like the x there. And replace it on the right by x minus 1 as well. As long as x minus 1 is close to 0, which means x is close to 1. So you can find sometimes linear approximations for other functions based on a given linear approximation. By just like essentially doing like a horizontal translation is what we're doing. In terms of differentials, you can write it like that. Questions?
Sorry, just going back to sine of x and cosine of x, do those all relate to the trig identity sine of x plus the cosine of x is equal to 1?
You mean sine squared plus cos squared?
Oh, yeah.
Yeah, I mean it's related to that.
Okay.
That you can say it's related. Yeah. It doesn't prove it.
Yeah.
But it's related. Here's one where I took a to not equal 0. I took it to be 1. 1 over x to the p, x to the negative p. It is analogous to this one, and I could relate it to this one. Actually, this one even works when p is negative, actually. Turns out this is true. I'm separating it as a different one because it's sort of useful in other circumstances. So there I'm taking the a to be 1. Let's confirm this works. F of x is x to the negative p. F prime of x then would be negative p x to the negative p minus 1. A is taken to be 1 now, not 0. F of 1 is 1 to the negative p, which is 1. F prime of 1 is negative p times 1 to the negative p minus 1, which is negative p. So now I get f of 1 is 1, f prime of 1 is negative p, and a is a 1, and this simplifies to 1 minus p times x minus 1 in parentheses. Essentially, the graph of x to the negative p, assuming p is positive, really, same as 1 over x to the p. It looks like this, and at 1, the tangent line has a slope equal to negative p. That's what's going on. And the output is 1. Okay? I'm not going to test you on these, though you should be able to derive any of those approximations in the same way that I've done here. But what I'm saying is, for future math and science courses, engineering, these are often useful. So it's worth trying to remember to some degree. Anytime you talk about approximation, you got to talk about error, really. If you want to be getting to technicalities. What is error? Well, let's consider an example. Let's use a tangent line approximation. In other words, a local linearization. It means the same thing. To approximate the cube root of 10 and give an upper bound for the absolute value of the error. Actually, I'm not going to do quite what I'm saying there. I was thinking about a different example later on. I'm not going to give an upper bound for the error. I'm going to give an approximation. There's another example we'll do later where we'll give an upper bound. What are the function and the derivative that we need to consider? F of x is the cube root of x, x to the 1/3, and f prime is its derivative, 1/3 x to the negative 2/3. So, you know, one way to approximate things like this is with Newton's method. We talked about that last week. Newton's method is a really good method. This is another method for approximating something like this. This is not quite as good as far as getting a good approximation, but it is still important in terms of later ideas that we get into. What should we use for A? We're going to use the linearization of tangent line approximation. We should pick A appropriate. Should we pick it to be 0? That's probably not a good idea. 8 or 10 is kind of far away from 0. Should we pick it to be 1? 10 is still kind of far away from 1. We could pick it to be 10, maybe you might think, but we're trying to find the cube root of 10, so that doesn't seem to help. What number relatively close to 10 has a simple cube root? 8. Choose A equal to 8. That's a number relatively close to 10 that's got a fairly simple cube root. That's why I chose A equals 8 here. What's the tangent line approximation? Here it is. A is 8. I'm using the exact same formula that's on the board over there with A equal to 8. And now it's just a matter of plugging the numbers in. F of 8 is the cube root of 8, which is 2. That's why there's a 2 there. F prime of 8, you really get 1 over 3 times x to the positive 2/3, if you write that as one fraction with the x to the positive 2/3 in the bottom. 8 to the positive 2/3 is 4, right? Because it's first take the cube root of 8 to get 2 and then square it to get 4. That's what 2/3 powers mean. 3 times 4 is 12, so you get 1/12. Therefore, you could try to approximate cube root of 10 by plugging in x equals 10. Let's try to do a rough approximation without a calculator. If I plug in x equals 10 here, I get 10 minus 8 is 2. 2 divided by 12 is 1/6. Plus 2 is 2 and 1/6. I don't know if you remember what 1/6 is as a decimal, but it's about 0.1, well, it's 0.16 repeating, with this, just the 6 repeating. We're approximating the cube root of 10 to be 2.16 repeating. Is it that exactly? No. This is an approximation. What is it more accurately? With a calculator, it comes out to be 2.15443, etc., etc. I'm not bothering to write more. It's an irrational number, just like square root of 2 is. So we're off a little bit. What's the error? We will calculate an approximate error here. The error is actual minus approximate is 2.15443 minus 2.16667. I really rounded there on both of those. To get a negative error, negative 0.01224. The negative error just means that the true value is underneath the approximation. This error equals actual minus approximate is true in general. And it's very fortunate because it goes in alphabetical order. AC comes before AP. It's actual value minus approximate value. Technically, these are not actual. That's not an actual value. That's an approximation as well. That's why I put approximate equal to symbol there. Actual, approximately actual minus the approximation that came from the local linearization. It's negative because the actual value is below the approximate value. More on error. We can consider the error function. We talked about this last week. Remember this? That was an error at some specific value of x equals 10. But we can let x be arbitrary. The error in general is f of x minus the L of x function, the actual minus approximate. Which, well, if you plug in the functions, is this minus that. That is a function of x. You could graph it. We will graph it. It turns out that that's approximately equal to f double prime at a, which is 8, divided by 2 times x minus a quantity squared. Again, a is 8. Where am I getting that? Well, it's something in the book. If you happen to look on page, it's in section 3.9. It's page 171 in the box. The error in using a linearization to approximate a function f of x near some number x equals a is approximately f double prime of a divided by 2 times x minus a quantity squared. A is 8 here for us, right? I went ahead and calculated the derivative at 8 and divided by 2, and I got this limit. That's worth checking after class. The function we're dealing with is x to the 1/3 power. You got to find its second derivative, plug in 8, then divide by 2, you'll get about that. Check it out after class. Therefore, the error at 10 by this approximation is about negative 0.014. Now that's not the error we found from the previous slide, but it's fairly close. According to this approximation right there, the error is approximately that. What did we get from the previous slide? I'll come back to this one in a second. What did we get from the previous slide? We got negative 0.012 approximately. Right here. Now from this new slide, we're saying, based on some theory that we're not getting into, that the approximate error should be negative 0.014, not too far away. So this is based on some theory. We're not getting into the theory here. We're just trusting it. There's a theory, some theory that can show this approximation is pretty good. Then you can graph it to see it. The blue graph is the cube root function. A is 8, that's where the black dot is, at 8, 2. The red line is the linear approximation. We're trying to approximate the second coordinate on the blue graph when x is 10, right about there, with the second coordinate of the red graph. They are pretty close together. They're practically on top of each other. Down here, the brown graph is the error function, f of x minus L of x. It's negative because f of x is below L of x. And the green graph is this quadratic, this negative 0.0035 times x minus 8 quantity squared. This thing right there, that's in green. And you can see the brown and green graphs are pretty close together when x is close to 8. They actually would touch the axis right there at 8, even though it doesn't quite look like it. They would actually go through 0 right there, when x equals 8, which makes sense. Plug in 8 there, you get 0. Okay. This leads into what is called Taylor series ultimately, that I'm just going to introduce right now. You're not going to have to know about Taylor series in general, but this kind of problem-solving process I'm about to show you is something you should be able to do, though maybe not in quite such a detailed form. There's a lot of writing on this slide. It's probably worth not writing it down, so you can focus on what I'm saying. So there's a lot of writing. What if I asked you to find a quartic, a 4th degree polynomial function like that, g of x equals a times x to the 4th plus b times x to the 3rd plus c times x squared plus dx plus e, I get tired even saying it, that approximates the cosine function well when x is close to 0. What do? You just guess? Well, that is a strategy. It's not a very efficient strategy, but it is a strategy. A better strategy that ends up being more efficient is to try to match up the function values f and g at 0. In other words, since cosine of 0 is 1, and g of 0 is capital E better be 1. But don't just match up the function values, match up the derivative values. And how much, but not just the first derivative, but the second derivative, and the third derivative, and the fourth derivative at least. The fifth derivative of this would be 0, actually, if you think about it. Keep taking derivatives, it gets lower and lower power. And so once you get to the fifth derivative, it's the 0 function, which doesn't seem so helpful. But maybe we can just match up the first 4 derivatives. Here are the details of the calculations. Again, don't write this down. If f is the cosine function, its derivative is negative sine, which means its second derivative is negative cosine, which means its third derivative is back to sine, which means its fourth derivative is cosine. Back to the fourth derivative of cosine is itself. Wow! Isn't that wild? It's true. It's cyclical. And the same kind of thing happens with the sine function. Its fourth derivative equals itself. Now plug in 0. You get 1, then 0, then negative 1, then 0, then back to positive 1. How about the derivatives for g? If g of x is this, its derivative is this. I'm confident you can do that if I asked you to. Check it in your mind right now. Right? Power rule in linearity. The a, b, c, d, and e get carried along for the right, although the last e is a constant times x to the 0, you might say. It differentiates to 0. But with every other one, we're using the power rule. We're bringing down the powers and subtracting them from the exponent. Bring down this 4, get a 4a, make the exponent go down by 1, or 3, etc. Which means the second derivative, third derivative, and fourth derivative are what you see here. And yes, the fifth derivative would be 0, but I didn't bother writing it. Now plug in x equals 0 into all those, and here is what you get. You always get the constant term, right? G of 0 is just capital E. G prime of 0 is just capital D. G double prime of 0 is 2C. G triple prime of 0 is 6B. And the fourth derivative of G at 0 is 24A. The fourth derivative is a constant function. Make these derivatives equal these derivatives and solve for A, B, C, and D, and E. And what do you get? You get A is 1/24, B is 0, C is negative 1/2, D is 0, and E is 1. This is the fourth degree polynomial we're after, and there's a pattern there. 24 does happen to equal 4 factorial. 2 does happen to equal 2 factorial. I'm purposely doing that because if you continue this process and get even higher degree polynomial approximations, the pattern continues. How about the graphs and the error? How well does this approximation do? Again, probably too much to write on the slide, just think about it with me here. How big does the absolute error, which is the absolute value of the error, get over a given closed interval centered at a equals 0? Once again, the error is actual minus approximate, f minus g. G is that fourth degree polynomial approximation. Its absolute value is called the absolute error. It turns out there's some theory that says the absolute error in this situation will be less than or equal to this quantity over an interval of this form from negative b to positive b. I'm not saying what b is. So, for example, if b is 2, you get this. Okay? This is just some theory. You don't have to know where this theory comes from. You're just trusting me on this. There's some theory that gives an upper bound for the absolute error in this case, not just an approximation. Upper bounds are better because they're real precise. Approximate and equal to symbols are not very precise. And let's see how this works out with graph in this situation. The blue graph is the cosine function. The red graph is this fourth degree polynomial approximation. Look how well it does when x is near 0. The brown graph is the error, absolute error function. It's very, very close to 0 when x is close to 0. And if we take b to be 2, we're guaranteed that the error, absolute error, is always less than or equal to this number. If you look at the brown graph between -2 and +2, its outputs are very small. They're definitely less than 0.2667. That seems pretty cool. Here's something even cooler. I have to tell you a little story about this thing here. Oh, wait a minute. Did I forget? Oh, you know what? I have to do something. Let me get that. Okay. I'm about to show you higher and higher degree polynomial approximations to the cosine function in an animation. And a little story, I showed this animation once to somebody about 15 years ago. And like 5 years later, they came back and told me, Dr. Kinney, when you showed me that animation, it changed my life. I was like, whoa. So I'm about to show you an animation that changed somebody's life. It may not change your life, but it changed somebody's life. What is the animation? It's this. Oh, it's not going to work. That's no good. Oh, I got to enter this here. Now, okay, here we go. Ready? Flapping the wings, the higher and higher degree polynomial approximations to the cosine function. It's so beautiful. And it changed somebody's life when I showed this. Isn't that wild? Just by matching up function values and derivative values, higher derivative values. How high is the degree of this going? I plugged it in as a summation here. I'm letting n go up to 12 here, which means the sum has 13 terms in it here because I'm starting k at 0. The highest power is 2k power when k is n, which is again 12. 24th degree is the highest degree of real time. When n is 12, that's a 24th degree polynomial in red. That's an approximation of the cosine function. I wonder if this is how they program calculators to calculate cosines of things. Maybe. You ever think about how do your calculator know what the cosine of something is? What? How do you make a circuit calculate cosine? It is based on additions, subtractions, multiplications, and divisions, which are relatively easy to program into circuits. This is related to how calculators and computers compute things. Okay. To end today, let's talk about a few theorems, but we only have a couple minutes to talk about them. I'm going to talk about them more on Monday as we review for the test. Since we're not getting into very much depth, I can't get into very much depth about them on the exam, but there might be a little bit, maybe some true-false questions or something related to them. Okay? Just some theorems. For sake of time, maybe it's best not to write these down again. Just listen and think. This is called the increasing function theorem. It says if f is a function whose derivative is always positive over some open interval here from a to b, that's not a point, that's an interval. A is the left endpoint, b is the right endpoint. Open meaning don't include the endpoints. Use parentheses. Then the function f is strictly increasing on the closed interval from a to b. That's closed interval notation. Square brackets means include the endpoints. I'm implicitly assuming f is defined on the closed interval when I say that. The decreasing function theorem says if f prime is always negative on some open interval, then the function is strictly decreasing, going down. Increasing means goes up, decreasing means goes down as you move from left to right. Again, I'm implicitly assuming it's defined in source of the beginning. There's also something called a constant function theorem. Skip these two for the moment. If f prime of x is always 0 on some open interval, then the function is constant on the closed interval from a to b. That should make intuitive sense. If the derivative is always 0, if the tangent line is always horizontal, what else could the function be but be horizontal itself? Proving these seemingly obvious theorems takes actually a ton of work. They're pretty hard to prove if you try to start from real basic properties of real numbers. I will say also, before we get into some more details on Monday, that the converses of these theorems are technically false. What's a converse? Converse of the first theorem, don't put stuff away yet, be with me here, it's distracting for people, would be that if the function's increasing on the interval, then it must always have a positive derivative. That's actually not true, even though it sounds true. Converse just sort of switches around the order of things. If the function's always increasing, is its derivative always positive? It's actually not always true. I'll let you think about that over the weekend. We'll talk about an example. This example on Monday.